yesterday we discussed orthogonality, and we also discussed some normalization procedure, right? So let's first look at the orthogonality. As we discussed, vector v1 and v2 are orthogonal when we satisfy this condition, right? So these two condition is like when you take autocorrelation, for example, of v1, then you're going to get some value. But when you take a cross correlation of between these two signals, or inner product of these two vectors, two different vectors, then it's going to be 0. What that basically means is that when you look at the definition of inner product, the inner product is going to be v1 amplitude, v2 amplitude, cosine theta, right? Cosine theta, theta is the angle between these two vectors. So in order to make this in order to make this 0, amplitude can never be 0. This one cannot be 0. So that has to be 0, right? So because of that, the only condition in order to satisfy these things is that theta is 90 degree. Which means that when you draw this visual way, we can see that the angle between these two vectors is 90 degree, right? That's all the same thing, right? This is the only condition that you get this condition. That's what we call as orthogonal. So if these two vectors are orthogonal, or these two signals are orthogonal, then we always have the angle of 90 degree, which means that when you take a projection of v1 onto the v2, projection will have a 0, right? The projection have has nothing. If you have a little bit of projection, for example, when you project it, you have a projection vector like this, and that projection is not 0, that means those two are not orthogonal, right? That's all the same thing. Orthogonal means cross correlation is 0. That basically means a projection of one vector to another is 0. That's all same thing. Okay? So this is just calculation of dot product and correlation. And this is the inner product. So let's keep moving here. So given that this Grove-Schmidt procedure tells you how to make some of the vectors, some of the non-orthogonal vectors to be orthogonal, right? For example, when you have a u1, u2, u3, right now these three vectors are not orthogonal each other. When you draw the u1, u2, u3 vectors, you can see that between these two, the angle is 45 degree, right? It's not 90 degree. So those are not orthogonal. What we want to do is we want to make these three vectors to be orthogonal. Okay, we want to make them orthogonal. That's what we want to do. And this procedure tells you how to do that, right? How to make these three vectors to be orthogonal. So how to start is we want to take one vector, one of these, any vector is fine. So we can take this one as a starting point, and we take a normalization. Okay, normalization. Then from this, right now this does not have a power 1, right? This one has a power 2. So we want to take a normalization, and we're going to change this one into this. And we'll call that as a W1. So W1 right now this is U1. Let's say U1 is this vector. And W1 goes into the same direction, but it has amplitude 1, or the power 1. So that's W1, right? But W1 and U1 are going into the same direction. It's the same vector. Simply U1 is an extension of W1. Okay, W1 has a power 1, or norm 1. Okay, so that's W1. And from this, what we want to do is we have another vector called the W2. Between U1 and U2, the angle is not 90 degree, but we want to make them 90 degree. Okay? We want to make them orthogonal. So how to do that is from U2, you are subtracting projection projection of U2 onto W1. Okay? You are trying to subtract projection of U2 onto U1. For example, so when you take a projection, this is a projection, that is a projection, because think about it, we have light here, we are making projection like that, right? So we have a shade, that is a projection. So now U2 minus this projection vector, that's going to be this vector, right? Now we see that we have a 90 degree. This new vector, we call that as a W1. Actually, that's not W1, that's V1. W1 is after normalization. This is V2. V2. This V2 vector is now orthogonal to W1, right? Because we subtract projection out. This is a projection, we removed it. So therefore, you remove this projection, then there's no projection. Projection is 0. Projection is 0. Projection is 0 means orthogonal, right? So therefore, this W1 and V2 is now orthogonal, but after that, what we want to do is we want to take a normalization of V2 and take W2 here. So when you look at the W2 here and W1 here, let me look at it here, W1 and W2. Those two are now orthogonal and both are size 1, amplitude power 1, right? You can keep doing the same thing. For the third one, we again have a third vector, U3. So from this third vector, we're gonna subtract the projection of U3 to W1. This is another projection of U3 to W2. So we are taking two different projections. Same idea, basically. Keep doing same idea. Then you're gonna get V3, and this V3 is another direction, but the angle between the V3 with W1, V3 with the V2 is going to be 90 degrees. So these three vectors all have a 90 degree each other because you remove the projections. So that's V3. And the last step is to take a normalization, but this one is already normalized. So we're going to get the same 0, 1, 0. That's going to be W3. So finally, that's the answer. That's what we call as orthonormal, because this is the amplitude power 1, or norm value of 1. So that's orthonormal basis. So we now have these three bases. So based on these bases, now remember that these bases, so this is a original x, y, z, right? U1 is somewhere here, U2 is somewhere here, U3 is somewhere here, something like that, right? These three vectors are not orthogonal, but if we make these orthonormal bases, which means that we are making another x, y, z basis. Like this is one basis, this one, W1, and that is another basis, which is 90 degree. That is this one, and this is that basis, right? Again, 90 degree, 90 degree. So if we use these three bases, meaning that now this is like x, this is like y, this is like z axis, right? We are basically rotating like that and make a new x, y, z basis. Once you do that, then based on this new x, y, z basis, where is U1? That's here. W2, root square 2, 0, 0. That's the position of U1 in the new axis, new x, y, z. Actually, U1 is on the x-axis, right? So that's the position of u1 onto the new xyz. Same here, right? This is like 1 over root square 2, 1 over root square 2, 0. That's the position of u2 in the new xyz position. Same here. This is like root square 2, root square 2, 1. That is a position of this u3 in the new xyz. So based on this new xyz position, right? New xyz, these u1, u2, u3 position is now different. This position, right? u1, u2, u3, they stay in the same position. They never move, right? We are not going to move. This one still there. This one is still there, right? Those u1, u2, u3, they never move. They are still there. What is moving? Axis. The xyz is now moving, right? xyz. We no longer use this xyz. We use this xyz. So therefore, we have a new position. Does it make sense? But with this new position, new xyz, now the u1, u2, u3 are orthogonal. They are now in a new position, and those three guys are now orthogonal. So this is a procedure of orthogonalization. Okay. Okay, what if we use this one as a starting point? Remember I told you that you can start from any vector, right? In this example, I started from this vector. But what if you use this vector as a starting point? You can do that, right? In that case, what's going to happen? Let's think about that. Let's go back to original picture here. So we have u1, u2, u3. What I want to do is I want to use this one as a first vector. Okay, first vector to start. What's the first thing to do? We want to take a normalization. This is already normalized. So this is going to be then the first w1, right? So now this is going to be w1, the first basis. So based on that, what we are going to do is that we are going to do the same thing. So now this is going to be W1 is going to be 1, 0, 0. Okay. So from that, what we are going to do is U1 minus U1 W1 W1, something like that. Okay, let's call this one as W2. Since we start from U2, let's call this one as W2. Then this is W2, W2. So that's W2. So we're going to calculate this one. What is this? That's going to be the projection of U1 onto W2. So we are going to make this U1 projected to W2, right? And this U1 minus this projection. That is projection. So once you take a U1 minus this projection, what do you get? You're going to get this, that vector. That vector is going to be V1. And from this V1, we normalize it, and we're going to get W1. Okay, so we're going to get new W1 here. Do the same thing for the third one. So eventually, when you keep doing it, what you're going to get is probably you're going to get this one as a basis. Probably something like that is a basis, or something like that is a basis. Just example, right? So you're going to get new basis, not this one. These three bases is when you started from the first U1 as a starting point. If you started from U2, right, and do this calculation, now you're going to get the new basis, another basis. right? Yeah. So what that means is Gram-Schmidt procedure does not give you a unique solution. If you start from this vector, you get some basis. Starting from another vector, you may get another basis. Okay? Yeah, so that's the Gram-Schmidt procedure. Then what is a QR factorization? This QR factorization is very useful, especially when you do the normalization. Here in the QR, how to do that is we collect all the column vectors, but this one is U1, U2, U3. Put them together, make a 3x3 matrix. Using this 3x3 matrix as an input and put that into the QR factorization, what you're going to get is you're going to get Q matrix and R matrix as the output of the QR factorization. Okay, QR factorization is simple signal processing tool. So you can run it in MATLAB or any other signal processing tools, right? So you can simply run it. Then you're going to get the Q and R matrices. And both are 3x3 matrix. But what we can notice is that always the R matrix is triangular. It can be upper triangular or sometimes it can be lower triangular, but always it's like a triangular matrix. Okay? And in the Q, you have 3 columns, and these 3 columns are same as the basis. So using these 3 columns as a basis, these 3 are the position, the new position of your own original vectors. So now these are new vectors, like this is original vector U1, U2, U3. Based on this, when you run the QR factorization, these 3 vectors in the Q matrix, those 3 column vector work as a basis, and based on that, now you're going to get the new position of these 3 vectors. So simply speaking, it's like a rotation. This is the original position of U1, right? And using this new basis, you are basically rotating XYZ. You are getting new XYZ position, XYZ space. Based on that new space, this U1 appears in this position. So they are new position. It's basically the same as the previous slide, Gram-Schmidt procedure, right? But we basically use another technique called the QR factorization, but the answer is the same. Okay. So that's a simple procedure in order to make orthogonalization. Okay, based on that, let's move on to some discussion on the pulse modulation. In this slide, what we are going to look at is some basics of pulse modulation. Remember that we discussed a pulse modulation, right? We had a pulse amplitude modulation, pulse width modulation, PWM, also PPM. Those are the pulse modulation. Now in this slide, you are looking at the pulse amplitude modulation, meaning that your amplitude has information. But this is like a special case where this is binary PAM, binary pulse amplitude modulation. What that means is we have only 2 different amplitude because this is binary. So original information is always either 0 or 1. Basically, this is binary, only 2 different information. Right? Since the amplitude has information and our original information is binary, we can only differentiate 2 different levels. This level means S1. That level means S2. Okay? We have only 2 information, binary, right? 2 information, S1, S2. This kind of signal is often called as an antipodal signal. Antipodal. Why do we call antipodal? Antipodal basically means we have a different sign. You can see that, right? Let's see here. This is a plus some value. This is minus same value. So the difference between these two is that actual magnitude is same, but this is a positive, this is a negative. Like this is 1 plus 1, this is like minus 1. Same amplitude, but sign is different. That's why this is called the antipodal. Anti means reverse, right? Pod means sign. So antipodal means a different sign. So this is like a special case. Okay? Binary, but antipodal signal. This is very common. Later, we're going to learn binary PSK. Okay, we'll look at that probably next week or so. BPSK modulation looks exactly like this. Okay, looks exactly like this. So one symbol has a positive value. Another symbol, by the way, we call this one as a symbol. Symbol. Okay, we call that a symbol. One symbol has a positive value, another symbol. The other symbol has a negative value. So that's why you call this antipodal signal. BPSK works exactly like that. This is an example. Let's say we want to transmit S1, S2, S2, S1, something like this, right? This is a sequence of symbols. By the way, what is symbol? Yeah, that's a message, but when we call the message, let's call that as a message. Typically, when we say message is a sequence of bits. Or even before that, it's just analog information. That probably is the original message. Okay? Some kind of analog signal, like that. This can be my voice, or this can be some kind of music. Whatever information you want to transmit, that is message. So we always started from message. So eventually this kind of original message needs to be digitized. And somehow it has to be converted into 0, 1, 1, 0, some bits. We call that as a bits. So how do you change that? How do you change this analog into digital? That's what we learned. There are many ways, right? Delta modulation or PAM. There are many ways. PAM is a little bit different, but this message, the easy way to do it is we put the A to D, AD converter. AD converter will convert analog to digital. Inside the ADC, we learn the sampling, quantization, right? All of those processes, okay, take place here. So change these analog to digital. Okay, that's what we discussed earlier, ADC, and even some PCM, DM, all those things. So from that, we get bits. These kind of bits now go into modulator. This is like a digital modulator. Eventually, you're going to get symbols. That's what I call as a symbol. So bits is not going to be transmitted. What you are transmitting is symbol. Okay? You are not going to transmit bits. So how do you change bits, or how do you convert bits into symbols? That is part of a modulation. So inside the modulator, depending on what modulation you use, sometimes you can use BPSK modulation, QPSK modulation. There are many different modulations. So depending on what modulation you use, you have a different mapping. But if anyway, bits is now converted to symbols, and these symbols is now transmitted over the air. Okay? So eventually symbol is transmitted. And that is symbol, S1 and S2. This is just an example. What is this? What is exactly S1? That depends on the modulation. Okay? We'll talk about the details later. But anyway, that is a symbol. So symbol is different from bits. This is not the same. Okay? Not the same. This is just an example. If you have a binary PAM, how to do that is you have a sequence of bits. When you get a sequence of bits, when you look at 1 bit by 1 bit, and if this bit is a 0, we transmit it as 1. If you have 1, you transmit it as 2. This is like a simple mapping. That's the case of this. So original information, in this case, original means this one. You have a bit sequence, but every bit, when you look at every bit, it can be either 0 or 1. So depending on which bit you have, you are transmitting one of these. And this is S1. This one looks like S2. Okay? So this is S1. We have some positive value. We have some negative value. And what is the TB? TB is symbol duration. This is symbol, right? This is symbol duration. But in this case, symbol duration actually same as a bit duration. Each bit has some duration, right? Time, TB, bit duration. But this bit duration is same as a symbol duration, in this case of binary. This is a binary, right? So 1 bit is mapped to 1 symbol. So it's like 1-to-1 mapping. So therefore, the symbol duration, bit duration, symbol duration is the same. Okay? The same as the, that's why we call it TB. B means bit. Remember, this is not always. This is the special case when we have a binary. Later, we're going to learn the QPSK. Okay? In QPSK, we have a different mapping. 2 bits. 2 bits will be mapped to S1. In that case, bit duration and symbol duration is different. Right? But binary case, it's going to be 1-to-1 mapping. That's why symbol and bit duration are same. Okay? That's a special case. So let's look at that. Let's say we have S1, S2, S2, S1, and that's the information we want to transmit. Since this is a symbol sequence, what was the original bit sequence? Here, in the symbol sequence, we have S2, S1, S1, S2, S2, S1, S2, something like this, right? So based on this mapping, what was our bit sequence? It was like a 0, 1, 1, 0, 1, something like this, right? This one was original, our sequence, bit sequence. Now, based on this mapping, 0 is converted to S1. 1 is converted to S2. Okay? 1 by 1. So that's why now we have this symbol sequence. This symbol sequence is graphically, it's like positive, negative, negative, positive, negative, positive, things like that. That's what we transmit. Okay? That's the idea. So this is a diagram over time domain. Over time, it's like a positive during this time. On the next symbol, you have negative. On the next one, negative, positive. This is time domain. This plot is called the constellation plot. Constellation. Okay, we're going to see constellation plot many, many times. Okay, later. We will see it many times. This constellation plot gives you an idea what does this symbol look like. And what you can see from this constellation plot is first amplitude, second phase, we get these information from constellation plot. So this constellation plot shows you that we have a 0 here. This point is S1. This is a positive, right? So S1 is a positive. And this is the bit energy. Actually, EB is the bit energy. E means energy, B means bit. So the EB is a bit energy. What about here? This is S2. This is negative. C minus root square EB. This is negative. Why do we put the S2 here? That's because S2 is negative. So this picture here and this picture here is same. The only difference is that in this picture, okay, I presented S1 and S2 in the time domain. This picture put this S1 and S2 in the constellation plot. That's the only difference. But these two are basically the same thing. Okay, these two are the same thing. So this is amplitude. This size is amplitude. If you have a larger amplitude here, let's say 2, just the example, right? If you have S1 here, what does that mean? You have a little bit higher amplitude. It's basically the same thing. Okay? And same here, negative, negative. And this one also has a phase information. Generally, here is a phase 0. What is the phase here? 180 degree. Or we put it as a phi in radian. Okay? So generally, in this case, right, the phase is 180 degree. So if this is a phase 0, that means this one has a 180 degree phase rotation. You know the phase 180 degree phase rotation of 180 degree basically same as put the negative sign, right? Or let's say reverse the sign. If the original one was positive and I add 180 degree phase and rotate, that becomes negative. Right? 180 degree means change the sign. Negative becomes positive, positive becomes negative. That's 180 degree. So all of these things are same thing. I'm talking about same thing in a many different way, but this one, all same thing. Okay? That's the case of binary PAM with antipodal signal. Okay, remember one more time. Why do we call antipodal? Because S1 and S2 have the same amplitude but different sign. Okay, that's antipodal signal. So this is one type of binary signal. Another type of binary PAM is like this. And this type of signal is a little bit different. In this type, this is not antipodal. Instead, we call this orthogonal signal. We call this orthogonal. In this type, it's a little bit different. This is simply called as on-off type. Maybe that's easier to understand, right? This means on. This is off. So we can start from bits again. So we have these bits. But now we have a different mapping. The previous mapping is like 0 becomes positive 1, something like that. 1 becomes negative 1. That was antipodal signal. That's what we just discussed. Previous slide. Now what we are trying to do is that we are going to do the different mapping. And now the new mapping is when you have a 0, then means we have on. When we have 1 in the bit, we have nothing. Means off. So that is orthogonal signal. So we can do this way, right? On-off type. We can do different mapping. You know, in this example, I put the 0 on, 1 off, but if you like, you can put it reverse. You can put 1 on, 0 off. It's up to you. You can do it that way if you like. So once you use this kind of mapping, now we are going to get these output. Right? So 0 is mapped to S1, 1 is mapped to S2, things like that. But we use this one is S1, this one is S2. So S1 means on, S2 means off. Off, on, off. We can do it this way, right? On-off type. So that's another way of mapping. S1 means on, S2 means nothing. Nothing means off. What if we draw this one in the constellation plot? Same way. This is a constellation plot. Okay, this is constellation. Right here is S1. S1 has some value, right? Some value. So positive value. So therefore, it's in here. That's a positive value. What about S2? S2 has 0. So it's supposed to be here, right? Here. But in this case, we typically put that in here. And that's why actually we call this orthogonal. Why this is orthogonal? Because this vector is orthogonal. That's why we call that. And there is a reason why I put it here, not here, okay? But that one we can explain later because we need to introduce some other carrier and things like that. This is a PAM, so the carrier is pulse train, right? Remember the PAM, PWM, all these things use the pulse train as a carrier. We use a pulse train as a carrier in this case. Okay, so this is a little bit different. Later, we're going to look at the constellation plot more detail. At that time, we're going to explain why S2 goes in here. But anyway, the idea here is that in antipodal signals, you can do +1, -1. That's how you can differentiate 0 and 1. But there's another way, orthogonal signal, you can do on-off type. Okay? So these are two different options, two different choices you can use for binary PAM. Okay, now let's move on to the next slide. Okay, this slide shows you some big picture. When you look at the communication system model, right? This is like a big picture. We have, of course, we have a transmitter, and there is also a receiver here, always. In between transmitter and receiver, we always have channel. Okay? Remember, what is ST? ST is always transmitted signal. MT is our original message. So your original message comes to the transmitter. Maybe this is your voice or any information you want to transmit. Put this information into the transmitter. Inside the transmitter, we always do modulation. This is a modulator. It can be AM, FM, or digital modulation, PAM, anything. So you are going to do modulation. And what modulation is best? How do you know? What is the modulation as a function? Function of what? Modulation is always function of channel, remember? Right? If the channel is wireless, we typically use sinusoidal waveform as a carrier. And if the channel, for example, is a chip-to-chip, we can use a pulse train as a carrier, right? And carrier is multiplied here. So carrier and modulator, these things is a function of channel. So anyway, we use modulator. And before transmit, we always use transmit filter. Okay, we'll talk about this one later. So we have a filter before transmit. Eventually we transmit into the channel. That is ST. So always ST is what we transmit. In the channel, we always have noise. And we are looking at AWG and noise, right? So that's going to be WT. We learned about WT, right? So that's what is added in the channel. That's what we receive right here. In the receiver, we probably have an antenna here, right? The first thing happening at the receiver is the receive filter. This is what I called as a bandpass filter in the last week, right? This is like a bandpass filter. So through this bandpass filter, your noise, WT, is rejected somehow, and now WT is changed to NT. Remember? So right here, what we're going to get is ST plus NT. ST safely bypass the filter, this filter, right? This is a bandpass filter, and your ST, your original signal ST, we have a bandpass filter here, bandpass filter. Your ST is inside this band, right? So your ST just bypass this filter. So this ST just pass, and we still have ST. But WT has has a constant power spectrum density. But that goes into the filter, and bandpass filter will reject some of the band, right? It only passes my band. Therefore, it's now changed to NT. So we have ST plus NT here. Now this signal, ST plus NT, goes into the demodulator. If you use like some BPSK modulation here, you're going to use BPSK demodulator here. Okay? So that's what we have, demodulator. Once you do the demodulator, next thing to do is a detector. What is detector? Detector is going to make a decision. What decision do you make? Let's say here, MT. Let's say your original message is analog. Then, as we said here, your original message eventually changes to bits, right? That is MT in this picture. You can think about that way. This one can be MT, that one MT, doesn't matter. But what I'm saying is your original analog will be digitized, and somehow it is changed to bits. And that bits goes into modulator. Okay, that bits. So right here, from the detector point of view, what we need to make is that we need to decide it's going to be either 0 or 1. If you transmitted 0 or 1, we eventually need to decide it was 0 or 1. That's the decision. Because that's what it transmits. We need to make a decision. So that's a detector. So this is a whole picture. This is a whole picture. But what we can do is that this is a little bit complex picture. So we want to make it simple. So let's simplify the model. This is a simplified model. Okay, the picture in here. Let's say we have ST. ST is this one. ST is coming into the channel. Inside the channel, what we do is we are adding noise. But look at this one. This is not WT. This is NT. Why is that? Well, because this is a simplified model. The actual model is this one, right? Actually, what is happening in the channel is that WT is the noise in the channel. But this noise, WT, eventually go into the receiver and go through the receive filter, and eventually becomes NT. So why not we just put them together put all these things together and remove this and skip all this and then make it simple like this. Because eventually it'll be changed to NT, right? So this is what is actually happening. But we are making it a model. So make it simple model. That's that. Okay? So we just make it simplified, and we just say that in the channel we basically add NT, and that's what we receive. So RT, what is received is ST plus NT, and this ST plus NT goes into the demodulator. Why? Because we already skipped all these things, right? So whatever you have here, ST plus NT now goes into the demodulator, and this part is same. So the whole picture is now simplified like that, okay? And from now on, we always gonna use this simplified model. But remember, this is the actual picture. We just make it simple because that's easier to do it. Okay, what we are going to look at from now on is that we want to look at the receiver part here. Okay, we have a receiver part. In the receiver, again, in the receiver, the main thing is demodulator and detector. Okay, demodulator and detector. And what is a demodulator? It is an inverse function of modulator. Okay, so we're going to learn one by one in the following weeks. So whatever modulation you use, BPSK, then you're going to use BPSK demodulation. If you use a QPSK modulation, you're going to use QPSK demodulation. So this demodulator and this modulator at the transmitter, those are like an inverse function each other. So we're going to learn it probably next week and the following weeks. What we are trying to do here, what we're interested to look at here is somehow the receiver design. Okay, some of the idea of receiver design in case of binary signal. So let's take a look at it. This is a very simple scenario. Very simple in the sense that we assume that we are transmitting binary antipodal signals. This is the assumption. We just learned the antipodal signal, right? Here. So this is what we are assuming. Okay? We assume that we use this mapping. 0, 1 is going to be mapped into positive or negative symbols. So that's an antipodal signal, and that's what we are going to use in this system. That's the assumption. When you use this mapping, okay, what is RT? RT is ST plus NT. ST is what is transmitted, and what does ST look like? ST look like this, either this one or this one. So when you go back, this is what ST look like, for example. Okay, ST looks like something like this. But in every position, every symbol, we are going to make a decision. Okay, for this symbol, we are going to make a decision. For this symbol, we're going to make a decision. So every decision is independent. Every symbol is independent. So if you look at only one symbol, it's going to be either positive or negative. Same for the next one, positive or negative. And we're going to make a decision for every symbol. So for each symbol, it's going to be this one or this one. That's it. That's it, right? So that's what we have here, RT and ST. Now the problem is we have a noise, NT. So what does RT look like? ST, again, ST will look like maybe this one or this one. What about RT? RT looks like something like this, or maybe something like that. That's going to be RT. Why? Because ST plus some kind of noise. Right? Let's add these two plus, then you're going to get something like that, right? So that's what you're going to receive. Now the question is, let's say you receive this kind of signal as RT. Okay? You receive this. This is RT. Let's say that is our RT. You received this kind of signal. There are so much noise. So we receive that kind of signal. Now, what is our goal? We want to decide if this is RT, which means ST plus NT, right? But that's what we receive. When you receive this, what we need to do is that we need to make a decision. Is this what we transmitted, or is this what is transmitted? Which one is transmitted? That's what you need to decide from here. So when you look at here, how would you decide? If you receive this as RT, then maybe this is transmitted, right? Maybe you can say that because this is there are a lot of positive value. Maybe this is transmitted. This is closer, right? When you receive this, maybe you can think about this is what is transmitted. It is more probable that this is transmitted. But what if we receive this? We don't know, right? Maybe this is transmitted, that transmitted, we never know. But we have to make a decision. That's a decision. That's what is happening in the detector. The detector will eventually make a decision. From this RT, we basically think about the probability. Okay? With the probability 60%, this one can be decided to this. With the 40%, this. Something like that. That's what's happening in the detector. And right now here, this slide shows you how to make a decision. Inside the receiver, we have two different ways. One is a correlation-based demodulator, and second is a matched filter. These two eventually is the same thing. Eventually, these two are same. But this is a correlator design. This is a correlator. What is a correlator? Correlator is doing correlation inside this box. So how if you calculate the correlation, you need to have two things. You need to have two signals. Only then you can correlate and calculate the correlation, right? You need the two inputs. So one input comes from here. That's actually RT. Actually, no. No, here. One input comes from RT. Where is the second input? This is the second input. That is second input. Then what is this one? This is this phi t is going to be either this one or this one. This one is going to be this one or that one. So what does that mean? The reason of we using correlator is to find out how much this RT is close to these two. If this one looks like a very close to this, we calculate the correlation. If this one is very much correlated with this, but with a little bit correlated with this, then we're going to make this one as a decision. Basically, we are calculating correlation. That's how you make a decision. So inside this box, we are calculating how much these two signals are correlated. So that's why we have two of them. Why do you have two of them? Because you are correlating with RT with this. That's this box. And you are also calculating receive signal with this. And you are calculating correlation between these two. So you are calculating correlation between these two. You are also calculating correlation between these two. So that's why we have two different correlator. So you're going to get to some value and some value. And that is correlation value. So let's say from here, we have a correlation of 0.9. This one has a correlation of 0.1. Let's say this one is positive value. This one is a negative value. And this one is RT. So using this RT and this one, put them together and calculating correlation. This one, RT with this negative value, calculating correlation. And that is the correlation value. In that case, eventually you are going to make a decision. And you get one value. So what's going to be your decision in that case? This is your decision. Because this one is a much higher correlated. So we're going to decide, oh, with a 90% probability, if this RT looks like that, very noisy signal. But still, using this correlator, we can decide, oh, with a 90% probability or 0.9 probability, we can decide that this one probably is transmitted. That's how we calculate it. That's the correlator. Does it make sense? We are calculating correlation. Since this is a binary signal, we have a two correlator. Because we have only two choices, right? We only have two choices. Because this is a binary. Eventually, we're going to decide this one or this one. This is simple binary. So we just simply correlate two of them. We're going to calculate the correlation between this and that, this one and that, and also correlation between this and that. So which one this is, which one is more close to this? That's the idea. Is this close to this or is this close to this? That's what we're calculating here. That's the correlator. So that's the block diagram view of the correlator. When you think about mathematics behind it, some of the equation behind it, this is some equation. This is a correlator. This block. This block is a correlation, but this is what we do. We have input, another input. We have two inputs, right? This is a received signal. This is that positive signal that we already know. We already know this signal. This is what we receive. So put them together and take an integration. This is how to calculate the correlation inside this block. We know that RT is actually ST plus NT. So put this S plus NT here. We can make two different integration. But this particular one, and ST, right? Original ST. We know that original ST is going to be only this one or this one. So this one or that one, right? So if we use this one as a ST, put it here, then this phi t, phi tau is also this one. So put these together, then we're going to make it square because it looks the same. And that becomes 1 because this one has a power 1. So we have a power 1. So therefore, SM goes down here eventually. And this part is that noise and this part. So this one basically tells you the correlation between noise and this signal. But that goes down to n. N is somehow a random variable. But that's a noise random variable. So it's going to be Sn plus n. So simply, the output of all the correlator becomes Sm plus n. This Sm is going to be this value. Let's say positive root square EB. And this one, negative root square EB. So Sm is going to be plus this one or minus this one. Okay. since we have a two correlator, right? In the previous picture, we have two of them, right? And the first one, we use this one as a phi. For the second one, we use a negative one for the input, right? So from this one, we get this one, maybe. The second one, sometimes we get minus. So we have two choices of SM. So that's the correlator, the equation of the correlator. Okay? So when you do this correlator, remember the correlation is very close to the convolution. What's the difference between convolution and correlation? Huh? Remember we discussed that last semester? What's the difference between convolution? Convolution, you need the two signals, right? You are convoluting two signals. So what's the difference between convolution and correlation? Inverse of what? Reverse of what? Let's say you have ST convolution with RT. And let's say you calculate the correlation of ST and RT. What's the difference? Difference is when you look at the equation, right? Maybe it can be T if this is a periodic signal. But when you do this, let's make it a picture here. It's easy to look at it. ST, let's say, looks like this. And RT, let's say, looks like just like that, for example. ST looks like this, RT looks like this, right? When you do convolution, how to do that is, first of all, you flip this, right? ST like that, still ST. And RT, you make a flip. And then slide. And calculating some correlation like that, right? That's going to be that's going to be convolution. This is convolution. What about correlation? In this case, it's a cross correlation of ST and RT. When you calculate the cross correlation, what you're going to do is that inside of integral, you are taking minus for the RT, ST, something like that, right? So the idea here is when you take a correlation, cross correlation, simply speaking, right? The correlation is calculating this way. You are taking minus and then put it in the convolution. So this is different, right? When you have this kind of calculation, first you put the negative in the time domain and then convolution. In that case, what is actually happening is this is ST and minus RT. In this case, minus is that what I'm saying is a flip, left to right. So this is R minus T. And I want to do convolution between these two. When you do convolution of these two, right? Convolution of these two. In that case, what do you need to do? You have to flip for the second one. Because convolution of these two, we're going to flip this. When you flip this, it becomes that. And that is actually original RT. So it's a slide. You're going to slide and calculating the correlation between these two. So correlation is going to be sliding between these two. Convolution is a sliding between these two. So the difference is this is different, right? So correlation is like a original signal. Original two signals are sliding and calculating, how much we have overlap. That's the correlation. Okay? So now going back here, original, we have a correlator here, and we have two inputs. One input is R tau. Second input is phi tau. Looks like this, right? And let's calculating correlation. We have phi tau. That looks like this. And the first input is R tau. That looks like something like that. That's what we receive. Because we have a lot of noise, we probably receive this kind of thing. Let's calculating correlation. In that case, how would you do that? Flip it, slide. Okay? When I say flip, flip and convolution. In that case, flip it again. So we are basically sliding these two. Eventually, right here, after correlation, what is going to be the output? Here is a 0, here's a TB, here's a 0, here's TB. Now think about correlation is actually convolution. That's what I'm trying to say, right? Convolution and correlation somehow is very similar. Let's go back to original, the basic. Let's say I want to do convolution of these two. And here is a 0, TB, 0, TB. What is the output? Let's take a convolution. What does it look like? You're going to get this. Here's a 0. Here's what? Here's TB. Here? 2 TB. That's the output, right? This is the output of a convolution of these two. Correlation is actually convolution. Only difference is you're going to flip one more time. But actually it's a convolution. So when you take a convolution of these two or correlation of these two, what's going to be the output? Output is something like this. It's from 0 to 2 TB. And the middle point is TB. Same thing. Okay? Same thing. So that's going to be the output right here as the output of the correlator. This is the output of the correlator that looks like this. Okay? That's what you're going to get here. So what is the next step to do? Always the middle point has a maximum point. And you are going to take a sampling. Sample at t equal to TB. We are taking sample here. Why here? Because that's the maximum point. We are taking sample at the maximum point. And maximum point is always at the TB. So just take a sample there. Then you're going to get this value, right? That value, we're going to get it here. That's the output. That's the whole idea. So let's go back to the previous slide. What we just discussed is this part. Okay? We have one correlator here, right? Again, when you have this correlator, we have one input here, second input here. This input looks like positive value. We have some noisy signal coming in. Then put that into the here as a correlation. But inside the correlator, we have a convolution. So the output right here is going to be somehow that kind of signal. And middle point is TB. That's why we sample at TB. Then we're going to get this value right here. Something like, let's say, plus 0.7. Something like that. Then you're going to get this. Same thing is done again for the second one. For the second one, we have a negative value. So put this noisy signal as a first input. This one goes into the second input. Now we are going to do same correlation, same convolution. Then what do you get here? In here, probably you are going to get something like this. And again, here to here, the middle point is TB. Here is a 2 TB. Here is a 0. And again, you sample it at the middle point, TB. So you are going to get this value. That value happens to be like something like this. So based on these two values, you are going to make a decision. Okay, when you look at these two values, you're going to make a decision. So if you have this kind of signal coming in, you're calculating correlation for these two, most likely you're going to get very high value, very small value here. Then what's going to be your final decision? This one. Why? Because this one has a higher value. Now let's think about another case. Let's say our RT looks like that. Okay? It's again very noisy signal, but we receive that. In that case, you do the same thing. Then what are you going to be the output here? Probably your output is going to be like that. Because this is negative value, you have a negative one. So negative value correlation, you have a more negative. And middle point is going to be TB. Here is 2 TB. And you sample it at the middle point. So you're going to get this value. Probably you're going to get something like this. What about this correlation? This correlated with this, you probably get something like that. Again, sample at the middle point, you're going to get something like this. So which one is going to be your decision? This one. So that's it. That's the whole idea. Okay, that's the whole picture. That's how the optimum receiver is going to work. That's your optimum decision. Okay, that's the idea. This one, actually, sorry about that. Yeah. Okay. So based on that, that's the idea. But 4시까지인가? 4시? Okay. Okay, we can continue next week.